and the PI on LIGO, and who has been the primary person responsible for making LIGO into something real that has a good shot at success. He's going to tell us both about the status and plans for LIGO, and also about the issue of the organization of large projects. This is something that high energy physicists figured out how to do long ago, and Barry is perhaps the world's greatest master at it.
Wow.
At least that's the impression of me and everybody else that I talk to. So we'll hear from the master. Barry.
I have no idea how to give this lecture, so I put together a bunch of random, semi-random, used things, I would say, not random, and it's best if it's interactive. So I would appreciate not worrying too much about some of the details. I'm not going to give you a cookbook how to run big projects, and I'm not going to give you a lot of technical detail about LIGO itself. So I have two jobs today. One is to tell you something about LIGO as a big project, and something about the status and where we're going in LIGO, and that's what I'll try to do.
So Barry, when we do interact and ask questions, did you, unless the question is
repeat it?
Could you repeat the question?
Yeah, sure. Remind me if I forget. Okay. So in order to do this, I thought what we need to do is actually to understand what we mean by large projects and how large projects are done in general, and then what's special about LIGO. So I'm going to actually do this, not so much how you run a big project, but kind of how large science gets done and what some of the main issues are as a scientist in large science and how it's different in different places. So we're going to get to LIGO as a science project, but I'm going to try to put it in a little bit of perspective. Generally, when we do experimental research, the traditional mode and the way most science has been done is the little thing I have at the top, and that is a single investigator in his laboratory who builds up some equipment, usually a certain kind of equipment that he's expert at that has some flexibility. It may be a low temperature lab, or it may be something that has some particular facilities. And the program's usually built around that, a series of experiments, students, and so forth in the laboratories. They can be different size, different number of laboratories. And then sometimes, just because of the way science develops, people turn things pretty upside down or start something special just because it's to attack a particular problem. So it's a combination in small science between things that might be more programmatic. You pick an area, and techniques and things that you're familiar and good at and stay ahead of the curve more or less in doing the research, or some developments in science drive you in a particular direction that you have. So an example of something that's closest that I can think of to this area is maybe the lab of Eric Adelberger in Washington, who does gravity, basic experiments on gravity, and recently has responded to, so he does various precision, very difficult experiments on gravity itself, and recently has responded to the idea that there may be extra dimensions that are detectable in gravity experiments, so that there's a particular approach that he's grabbed. For small experiments, the funding comes from a combination of two things: private funds, which may be large or may not be there, or may be small, and grants from the federal government, some combination. Usually an assistant professor starts and they get significant funding to set up a laboratory, which gives him this structure up here by the institution where he or she gets a position, and then usually the ongoing research support comes from federal grants. Usually. And the typical support, and there's huge error bars on this, but the typical support for some professor with his laboratory at some average university is about $150,000 a year. That supports the professor, his laboratory, maybe not all the setup equipment, but the laboratory itself, students, maybe his summer salary, a little travel, publications, and so forth. And for research in fundamental physics, there's three main support agencies. They work quite differently, as you'll see as I talk a little bit more. The National Science Foundation, and they're all I don't know exactly, the sizes are hard to tell you because it depends on what you define as fundamental. So the amount, or in case of NASA, how much is really the science compared to the bigger infrastructure. So the three main funding sources that are federal are the National Science Foundation, the Department of Energy, and NASA, and they all work very, very differently. I'll give you some sense of that. Okay, so this is the traditional mode that most research was done in up to maybe 50 years ago. And then slowly technology and the needs, the advancement of technology and the needs of using larger resources, both human resources, people, and equipment, drove people to larger projects that required teams of some sort, collaborations or teams. And that's developed now into its own cottage industry, if you want. And to the point where the appetites are much bigger than the number of things that we are capable of doing, would like to do, are much bigger than either the funding or the number of people around. And so there's a problem of which ones to do, how you go about implementing them, and so forth. And they're done quite differently in the different agencies. But just to give you a sense of them, of the different areas, astronomy is unique and different. It's the one area in fundamental science or fundamental physics that has a large amount of private funding, which makes it somewhat different than others, because the way you get private funding is a different scheme than how you get funding from the government, and it's sort of somewhat entrepreneurial. It depends where you are and whether you find somebody that gives the funding.
Can you give me an idea why it is that astronomy has more?
There's some tradition, but I think
the WMK Foundation gives money to build telescopes.
I think astronomy has held an interest in the public for centuries, while other areas of physics are a little harder to connect. And so the tradition was that it was always built privately. Other parts of physics that are funded, which I'm not really talking about, that are funded by private industry more, have a more commercial aspect. Certainly astronomy has none, but it has a certain tradition.
What's so interesting about it to me is that you're never going to build a better library than astronomy. It seems to raise such interest that people want to give money to it.
But this creates an incredible difference. The way NSF or government does things is so different than raising money privately that astronomy has communities that are different from each other. There's the privileged, in a sense, that are in a place like Caltech that have large instruments that came about privately and have time, and then there's the ones that are public that have a whole different set of rules about how they're used and what money's used in them and so forth. And those two don't interface very well. I mean, the Keck observatories aren't open to the whole community, so should the whole community's telescopes be open to those that have their own and so forth. So there's a tension that's there, but astronomy at least has a lot of facilities partially for these reasons. The support for space science is purely NASA, and now there's actually a little bit of support for instruments that comes from DOE that's in space science, and I'll talk about the way these come about in a minute. Particle physics is supported by both Department of Energy and NSF, and LIGO is supported by NSF but doesn't quite fit any of the models, as you'll see. So the models of kind of how it happens has some very special characteristics. Okay, so let's start from small science, which I said was a great success. First, the grants or the private funding of support, as we said, the research and the infrastructure. A key thing is there's what, in kind of the lingo that's used in projects, there's no direct account, or used in the government, there's no direct accountability. In other words, somebody doesn't give you $10,000 and then you report back what you did with it exactly and that you wrote and met your promises and so forth. Instead, you're given money to do research, and it's basically a trust system, and that is that you're given money because you convinced some reviewers or somebody that you should get the money, and then you're reliant on having done well at that, so that when you're peer reviewed after that, people feel what you've accomplished is worth reinvesting in you. And that's the scheme, and that's a very successful scheme. Basically, people are given money, they have flexibility then to more or less do what they want, not completely, but more or less do what they want, and then they could be 1 year, 3 years, some finite amount of time, and then they have to try again. And if they haven't done very well, they probably don't get another grant. If they've done well, they may get a bigger grant or more grants and so forth. So this system is a really good one, and it's one to emulate when you move into big science, and that is that the system is flexible. People can change what research they're doing depending on the scientific needs, and that it's really driven in general by the science itself, what you want to do scientifically, and new ideas. You can take and do anything you want in the lab. You don't have to go get them prejudged by somebody, and you can try creative things. You'd like to emulate this whole thing, and that's what I say when you do big science, and there's problems doing that. So the real issues are how you manage to get the good things that exist here when you get involved in large resources and the things that are involved in large science. So when we talk about large science, then we have first mostly special funding. In some cases, for the large laboratories, they have ongoing large equipment funding, so certain things they can do more, maybe not in a sense without asking for it from the government, but more or less they have some ability to carry out a certain level of things. But in general, any large project, something of the scale of LIGO or near the scale of LIGO, requires special funding for the equipment. That special funding, and this is one of the first places that is different for LIGO, in most cases actually comes somehow through connection to some sort of national facility or national lab. So most large science experiments or equipment are done through some sort of national facility that is embedded in CERN, Fermilab, JPL, something that's involved in that system. And so when we talk about how LIGO works in general and detail, there's a difference of kind of whether you're embedded in this huge national laboratory or national facility or doing it separately. In contrast to this up here, except for something like the Keck Foundation, which is not government, you're directly accountable, and it gets worse every year, basically by congressional dictate. When they give away money, they want to get measurement, they want to get accountability. Accountability is not so bad in building a large equipment, but it's getting extended beyond that. For example, the present administration likes things called performance metrics. And performance metrics are business lingo for how you measure how well something is being done. It's very hard to do that for research. So if you get a research grant, you want all this flexibility we talked about up here. How do you make promises and then measure against those? And there's a movement, basically, in this administration, at least in the government, to actually bring that down to the level of grants, so that somebody who has a grant makes a grant proposal with promises, and then they get measured against those. It's not so bad if you build an accelerator, you can measure how many protons you accelerate or something, but if you have a grant and you want flexibility, it's not a very good thing. So many of us are fighting very hard against that, or trying to find ways to rephrase the question so that you basically define it your own way. And so there's a lot of kind of clever people working on how to define these things like performance metrics for research. As I say, it's not so bad for building equipment. In large science, when you build large things, you again have a lot of peer review. It's done in different ways, but it's a lot of peer review like you had here, so that's good. But you also have a lot of review for other things, because you're responsible for how efficiently and how effectively you manage the whole thing, and where you spent your money, and that it was spent as you were supposed to, and so forth. So there's also a whole set of things which tend to dominate this one. That take all your time when you do a big project. The last thing, and the one that I want to spend a little time on, because again, it's where LIGO is different, but if you look at the bigger picture in terms of how you do big science compared to small science, it has to do with, it seems to me the rest of it is just kind of how you go about doing it all, really has to do with what you might call strategic planning, or the direction for a program, what constraints, what that determines about what science gets done, what flexibility there is compared to these nice words, how flexible you are, how much you can use ideas and so forth. You're in a system here where there's a lot of strategic planning, a lot of long-range planning, a lot of direction from above often, and sometimes some politics. So I'm going to talk a little bit about this, just to give you a sense of how that's done. And that doesn't really quite enter directly into LIGO, because it's not, you'll see why, because it's not in a defined field.
When you speak about high-level direction, you mean from the agency?
Yeah, yeah. So I'll talk a little bit about that. Okay, if we talk about then doing research in a large project, I want to kind of work from the back forward, or at least put it in perspective. You talk about research, we talked about so far about research, and you talk about the needs of a project, they're somewhat different, as you'll see. And the biggest problem isn't how you get somebody to do a particular task or how you're efficient. Most of us can figure out kind of how to do that, but it's how to smoothly evolve something that has to have the elements to be successful at something like a project, and yet somehow end up in a research environment as close to the one we talked about for small science as you can manage to do, because that's what we know that's successful in doing science. So that's the question we pose, is how to create an effective research environment for large science. And to me, that's always the goal that you're at. I think the other steps you can kind of figure out how to do one way or another, but you can end up in something that's that's organized the wrong way when it's time to do science if you're not careful. So the system that you want in the end should be flexible. You should, just same words, you should be able to create experiments that are driven by the science and driven by ideas. And that's the challenge, I think, and the biggest challenge in the whole thing. And there are different models of how to get there and how you do things in these different agencies. Then we'll come to LIGO. So in NASA, that problem is solved structurally by basically dividing. I'm oversimplifying when I'm doing these things because we don't have, everybody can find exceptions, but basically they separate the science teams for most NASA projects almost entirely from the project teams. That is, the people who build the project, who launch it, who do the testing, who put together the instruments are not the same people that analyze that look at the data or do the science, and they're separated from each other. These are a little closer, perhaps, for LISA than they are for a traditional NASA mission, but that's the natural way that it's done. And it even goes to the extreme, and this is again...
Even in LISA, they're really quite
separate. But at least the requirements are being set by them and not by a high-level NASA group, which is often the case in NASA projects.
The project management lives in Goddard.
Right.
The science in the United States is basically JP.
Yeah. Let me amplify a little bit. The actual traditional NASA model is to have some sort of scientists involved, but at a high-level panel, and this is what I called, I don't know what words I used, but coming down from above. They determine that you're going to do a science project. That group above also more or less decides how good it has to be. If you're going to measure gamma rays at a certain energy, what energy resolution you need, and what so forth. And then they basically go out for bids. They don't call it that. They call it an announcement of opportunity. So NASA decides up above at a high level that there's going to be a mission that looks at gamma rays at some energy, and then they make an announcement of opportunity. And people can compete for that. That's the equivalent of kind of competition. But it's very much like when we go out for bids for some building to be built or something. And so people compete by doing a design, and then there's a decision made on that. And then it's an engineering project. And then a scientific team is used later to analyze things. So scientists are involved at some very high level at the beginning to set criteria, and later LISA is a step better than that because it has a science team really working on requirements. So that's what I meant by it being at least a step from this very extreme mode. And NASA is traditionally really driven by engineering. It's a huge engineering operation, and science is a very small part of the budget. And that's what really affects this whole strategy. The last thing is this word open data. Whenever you spend so much money, the government is determined that it should be open to the whole scientific community. So how do you make it all open? We'll talk about this again in the case of how we're trying to do it in LIGO in a few minutes. But the way NASA does it is to make, as part of a mission, that the data in some form is documented well enough and put in a form that people who had nothing to do with doing it at the beginning can get access to it and analyze the data. That takes a lot of resources, a lot of documentation, and it's not the way we're doing it because I think it also has a certain inherent dangers that people analyze the data, don't know what they're doing, and it reflects on the project. So we have chosen to try to approach the same problem, which is government dictated, in a different way, and you'll see kind of what the strategy is that we're using. DOE is a bit different. It has the semblance of this by having something that NASA doesn't have. It has an umbrella grants. So the Caltech High Energy Group has an umbrella grant. It works very much more, it's a group of professors, but it works much more like a normal grant. That doesn't have all these performance metrics and so forth and so on. It has more peer review of the grant itself, and a lot of the internal things that have to do with DOE-funded science then comes from ongoing grants that go along. In these large projects in DOE, there's a huge amount of internal guidelines and reviews, some of which we use in LIGO, which means that the equivalent of the peer review, which is so important in small experiments, is always done at the level of publishing things, but at the level of kind of reviewing somebody's research, it's lost in this kind of thing if you're not careful. And a lot of that responsibility gets done internally, inside what we call these collaborations. So it's done, but it's done in a different way. So the reviewing of technical things that people do, or the papers, preliminary papers or results or things for conferences, or have a large amount of kind of internal review that's done inside the group working on a particular project. And these work in a very collaborative mode. Again, these are reminiscent to kind of what we're putting together for LIGO. Okay, the private ones, probably the best example here is the Keck Foundation, and that has a board. It has a thing called the CARA board. So the way that time is divided up, the way they decide what instruments to do comes from a board above, but it's basically not, I would say it's less peer reviewed than the typical government ones.
I have a question, just as a detail about the Keck telescopes. Who owns the land? Who sort of decided where?
University of Hawaii owns the land, and I think they get 5% of the time because it's on their property. I don't think they have any other obligations, but they got the Mauna Kea site through the University of Hawaii. Okay, LIGO, which we'll keep working ourselves toward, is NSF funded, and we have tried, in the way it's formulated, to, as I've kind of alluded to design it in a way that it'll evolve smoothly into something that at least mocks this standard peer review system, so that we have a system built into it that makes it have the things that at least some of us feel of what makes good science. And so we've moved away from this, for example, open data business. All right, before I get into that, let's talk a little bit about strategic planning, because I think it's the most interesting part of the whole thing, is when you get to big science. How is the science program determined for the next 20 years in the U.S. in fundamental physics? This should have said NASA. NASA is the one that's top-down, high-level planning committees. So they have very high-level planning committees. They review their strategy every 3 years. And basically then have the missions that are going to be done over the next decade or so at different levels and different sizes and different structures, and that gets evolved and updated through high-level planning committees. And those committees, of course, interact with the scientific community, but it's basically done by NASA listening to high-level planning committees.
So, for example, Sterl has been sharing.
Yes, right, right. But it's absolutely the opposite still of the guy down in his basement deciding what he wants to do, or the completely entrepreneurial system that happens in private funding. Astronomy has a different system. They use what's called the Decadal Review. It's put together by the National Academy of Sciences. It's done every 10 years, and it's extremely influential and successful. It's actually a very interesting thing to read. It's done starting from a very large group of people. I served on one piece of it last time, the review for 2000, and they divided astronomy into, 7 or 8 different subfields. Each of those subfields then had a process that interacted with the community and interacted with themselves, and were forced to prioritize everything in their sub-area. And then there's a higher level group that was somewhat smaller that made priorities of the list that the others did. And then you end up with a final set of priorities for astronomy. This works very well for astronomy. It works well in the sense that they can actually sit down and write priorities. It's a very hard thing to do for physics projects. And a very large fraction of them after a decade end up getting funded and done. So it's quite successful in that sense. It has a flaw for things that some of us care about, from my point of view, because you're forced to judge all projects on the basis of what they do for astronomy. And a lot of things are across their merit, including LIGO, has merit for physics and merit for astronomy. And how do you weigh one against the other? You're told in doing this is an astronomy study. So, for example, in the last one that I was on, some of the projects I was in the section called particle astrophysics. And so we had to deal with things like dark matter. Dark matter is a problem that's interesting to particle physics because it could be supersymmetric particles or axions or something. And it's interesting, of course, for astronomy. But the interests are different, and maybe the priorities are somewhat different. And we looked at the big neutrino array at the South Pole that was going in. And again, the interests are somewhat different. Some of the physics that does is particle physics. Some of it is astronomy, and it's a handicap for non-pure astronomy projects to be judged only on their astronomy. But that's the way it's done. Particle physics, and I'll show you this a little bit because I've just been involved, does its planning in a combination of the plans of the national laboratories that really dominate in terms of facilities, the program for particle physics, and what I'm using for a short word here, something called a roadmap, which I'll show you what it is in a minute. LIGO, again, is kind of outside of this. It's the same size thing, but we're not done inside a national laboratory like this. We're not done inside JPL, for example. And it's in a new field as well. So it developed it with a very different history, which I'm not going to go through, but I'll note that it came about because of Kip, Drever, Weiss, and Vogt, people like that, developing the techniques and slowly, let's say, getting enough interest and convincing enough people to make stepwise, first enough resources available to make a demonstration that was significant, which is the 40-meter interferometer here on campus, then eventually convincing the NSF and then getting funding for LIGO itself. So its history was quite different than top-down It's much more totally entrepreneurial, which is the only way you can do something that's completely outside the scheme. Okay, let me just show you what happens in high energy physics for the long range planning, because I've just been doing it. I'm going to do this quickly, but I just happen to have a short set of slides that they're out of, oh, I know. I wanted to go to something else. That's why I don't have it there. Okay, this is again just not so much interesting for LIGO itself, but how you do long-range planning for the same size projects as LIGO in a different field. So in high-energy physics, there's one big advisory panel that advises both the National Science Foundation and the Department of Energy. It's called HEPAP, High Energy Physics Advisory Panel. And it forms not every 10 years. It turns out in physics, we often have to look at things a little more look more short time scales than 10 years to decide what to do. And we change our minds, which is also different than astronomy. And so we form these panels every few years, but they're not all the same. They're different. In this case, this last year, I co-chaired this long-range panel, and it had a very broad scope. Sometimes it doesn't, because they're considering a particular project and whether to do it or not. But in this case, it was kind of to look at the whole field over the next 20 years and figure out a plan. So it's good to show you what that means. So a group of scientists that were not part of the agency had this set of questions to ask ourselves. So to reflect on the field itself. This is obligatory these days, which is, where do you fit in? But what is the field itself? And interestingly, in our case, we came out with a different definition for what high energy physics is than the traditional one. I'll mention that. What are the goals and paths that you use to accomplish those? In the case of high energy physics, do you use accelerators, or which ones, and non-accelerators, and so forth? We try to do a self-assessment. How is the field doing? What's happening in the near term, in other words, what's on the agenda already, and what opportunities do we identify in the long term, and how do we pick those? In the case of high energy physics, it's so big that you have to also consider all this stuff in terms of the international program, what's happening in other countries, and then to plot out some sort of plan that you can sell to the DOE and then the government on a realistic program that can get toward the physics goals that you want. And how do you pick the priorities as you go along? And not only that, how do you make sure you develop the technologies to keep going in the long-term future? So this is just kind of a list of questions. The strategy that we came to in this particular thing was to use a idea that was put forward in industry by Robert Galvin. And he developed, Motorola, he was the chairman of Motorola. And Motorola developed from kind of tube radios to cell phones over a period of years. So it's an example of an industry that has been highly adaptive and flexible and able to move in new directions as technology is developed. And so it's interesting to see how they did that. And it was really the philosophy of Robert Galvin who basically set this forward. Then he wrote a series of papers on why this would be good to do science as well, do science projects. And so we kind of used not just the word, but the ideas that he had. And that is that basically you create a thing that you call a roadmap. A roadmap then has all the roads that you can possibly take to get from A to B, but then you make choices as you go along. So the whole idea is how to make a roadmap where you start down the roads that look like the best path, but then you can identify the forks and make the choices when you need to make the choices to get from one place to another. And then you can go different ways, and you're not just set for the next 20 years. So in our case, where we were given the job of creating a program for the next 20 years, we wanted to, as much as possible, create it in a way that had these flexibilities and checkpoints. And I'll show you what we did in a very short way. So we looked at the field. So you look back at high energy physics and you can see the kinds of things that were done in the last 3 or 4 years. Evidence for neutrino mass, direct evidence for CP violation or antimatter-matter asymmetry in the B sector, which is very important, and the discovery of the last, we think, the last quark. And if you look at so you look back, that's about as short as I can do that. If you look forward, you can see a lot of things that are already happening independent of this panel. They are going to take a huge amount of data on the same experiment that did the CP violation. This is kind of the design of the machine, and it's already better than that. And they expect to take about, I don't know, I guess that's about 30 times more data in the next few years. So you can look at what that'll yield you in terms of not just seeing the CP violation, but the precision parameters that you can determine. The run that's just turning on at Fermilab will allow the next attempt to see if one can see the Higgs and maybe supersymmetry. And in the last few years, in fact today, is a very step forward for neutrinos. That neutrino oscillator, that is today, I don't know if people are aware of it, but Snow came out with a new result today. And so there's results that are coming out on neutrino oscillations, and one can see what's going to happen in the next few years there. So that's kind of the perspective to then look at the longer range. And what's happened in particle physics, and this is again assessing things as you go along and kind of changing, is the classical definition for particle physics is that this is set out in the 1950s, I think, is the fundamental constituents of matter and their interactions. That's what I learned when I was a kid, and you grew up with that. And the field is actually broader than that now. So the definition that we gave is more the study of matter, energy, space, and time. And the different areas that you look at and how they're heading in that direction. This is just kind of a cartoon, but heading in that direction. And then starting from these goals, the shorter term goals, things like hidden dimensions or connections to cosmology or unification, and using that to drive a physics program. So instead of it being driven from the top of an agency, our idea was at least to drive it from the science. The tools are a second thing. You really want a field to be driven by the science and not the tools. Particle physics is always in danger of being driven by the tools because you develop these huge accelerators, and then that starts defining the program instead of the program being defined by the science that you want to do. Particle physics right now is done in almost anywhere on accelerators. It's still the main feature. It's done in space increasingly, and deep underground, for example. So in terms of planning, you can plan for the next generation accelerator. This is accelerator since 1960, and you just kind of keep going up a curve. So that's almost a no-brainer as long as you know that going to higher energy really is the right thing in terms of the science. And so in our case, this one, the LHC, is the next particle. You notice we can't stay on the linear line on this log scale any longer, so that means accelerators are not technically as able to keep going. But the next one is still a big step forward. That's the Large Hadron Collider at CERN. And the one that we were considering the most is a linear collider, which is an electron machine. So there's large accelerators. And then there's the rest of the program. The large accelerators are so expensive if you're going to do one that it's just a separate issue. So in our case, we looked at the case of a linear collider. More interesting for LIGO is what, in the kinds of LIGO type projects, is a list of all the projects that people talk about, are doing, or are planning to do in particle physics that are of the scale of somewhere between 50 million and 100 and 500 million, say. This is what this scale is. So breaking those into different areas, if you talk about the energy frontier, then you're talking about experiments that are done in the highest energy accelerators. And there's a whole list of these, and there are different colors here. Colors being the yellowish color being ones that are either in planning or having R&D going on. So they're identified very early. One of these, for example, here is identified as a possible future project, but you see that there's no plan for it to change color during the next 20 years. So it's such a long research and development project that it's something you just invest in with the hope that it comes to fruition later. And other ones come later to change into a construction project and then a physics project. And then these are the other areas. And some of them come about, as I said, on shorter timescales. So for example, a particle physics experiment, I don't know, it's not particle physics exactly, but it's the group that takes ownership, is what's called the SNAP experiment. This is a follow-up of the dark energy experiment, which you'll see is on a time scale of doing R&D now, possible construction starting in just a few years, and with data after that. And that's very new. That's from physics discovery that's only 2 or 3 years old. So it's possible in our scheme and in physics in general to decide on something and actually have it happen in a fairly short time scale. These can't all be done. So the whole idea in terms of Galvin's scheme is that you have a whole list of opportunities, you invest in different ones, and when you get to these black things, you have decision points. And you have to develop a method that's as good as possible at deciding which ones to do and which ones not within kind of finite people and resources, knowing that the list is not going to all be done. And so we, in this case, worried a lot about that and tried to make sure that those decisions, there was no scheme. We've only kind of grown to where this has to be done, where these decisions can be made by scientists and not by, and it's very hard, as I said. The problem is that nobody wants to judge whether a CP violation experiment or SNAP is the thing to do. It's really apples versus oranges. So how do you decide the priorities? As a scientist, we don't really want to do that. But if we don't, then it's decided by the government bureaucrats, and you snicker, that's it. And they don't like to do it either. So they give too much to Congress, and then it's decided politically. So it's either decided by, I don't know which is the least of the evils, either the government bureaucrats or by the politicians. So it's much better if we somehow decide. So we're trying hard to invent a scheme where it is, as obnoxious as it is, people have to decide between things like SNAP and the CP violation experiment.
If it gets to the third stage, and you have to say, well, the SNAP is in West Virginia, and
well, yeah, that's right. That's right.
I'm a senator in West Virginia, so I'm going to get
right.
senators doing that.
And in developing these programs, you develop these long, this is how detailed this, I'll just show you one graph, how detailed the scenarios go. This is years from now. So this is 2000, 2019, and all the different colors are the projects that you saw in the previous graph, dollars, and how it adds up to more or less a constant budget or some reasonable increase. So that's how much you can fit in. So you can see how much of it, and you keep carrying this downstream. And a certain amount of it on the bottom, if you looked at the same plots for NASA, you wouldn't see very much of this on the bottom. And the difference is that if you build things to go in space, it really does have a finite lifetime. You build it, it operates for so long, then they stop servicing it and it's gone. If you build an accelerator, it has an infrastructure and it has technical people and so forth, and itself to feed. So a certain amount of this ends up being kind of the feeding of the field, and the rest of it are the experiments itself.
So what are those bottom two ones?
This is the LHC, and this is our model of Fermilab and SLAC, which you'll notice went down. So we were trying to get more into the science experiments and less as infrastructure, feeling that it had built up through the years. This isn't necessarily what the government will do, but it's what our panel tried to do. This is the same thing if you also add a new accelerator, which is the option. So anyway, that's how it's done in a mature field. And then we'll get back to LIGO. One sec.